Welcome to this presentation where we're going to focus on the chemical properties of the 4 samples provided. We're going to follow this plan, first introducing what electronegativity is, how this affects how atoms bond together, and how this in turn affects the physical properties of compounds. Then we'll look at the molecular stage, so how molecules are shaped and how they bond together, and how this again affects the physical properties of substances. So to begin with, we go back to what an atom is. So that an atom contains, these negatively charged electrons orbiting on the outside around a positively charged nucleus. Then, knowing this, electronegativity is basically the ability of an atom to attract shared electrons when it's part of a chemical bond, and the higher the electronegativity, the stronger the pull on the electrons. So fluorine, for example, is the most electronegative element and therefore the most reactive. And now in general, metals such as sodium will have lower electronegativity and they tend to lose electrons, whereas non-metals such as oxygen have higher electronegativity and tend to gain electrons. And this determines the types of bonds that are formed when atoms bond together. So for instance, if we look at the bond between 2 lower electronegativity, so metal and metal, this formed metallic bonding, which is a strong electrostatic attraction between positive ions and delocalized electrons, also called a sea of electrons. You can see that in the diagram on the left. And examples of metallic bonding can be, copper, iron, your typical metals. Now, if we have a metal and a non-metal, we have one with high electronegativity, the other with low electronegativity, and this forms ionic bonding, which is a strong electrostatic attraction between positive and negative ions where the electrons are actually transferred. So an example here is sodium chloride in this second diagram. Then lastly, if we have 2 non-metal elements, we have high electronegativity in both cases, and this forms what is called covalent bonding, which is where 2 atoms will share electrons for more stability. So an example of this is fluorine, and you can also see a diagram of what this would look like again on this page. So these bonds, influence the substance's properties, their physical properties. So this is summarized in this table here, but if we look in summary at metallic substances, for example, they'll have high melting point, high boiling point, high conductivity, they're malleable, ductile. All of these qualities make them very good in industry, for instance. Now, if we look at ionic compounds, on the other hand, they're usually solid at room temperature, but they're quite brittle and they're soluble in water. So this actually makes them really interesting for medicine and research, for example, in drug development. And now if we look at covalent compounds, we actually have 2 types. So simple covalent compounds, like we've just seen, will have much lower melting and boiling points. They're usually gases or liquids. But because of the potency and selectivity of those covalent bonds, they're actually really useful in medicine and research as well. Now, giant covalent bonds are a specific type, which is a network of 3-dimensional covalent structures, and because of these unique properties, they'll also be really useful in industry and research. Diamonds, one example. So yeah, now we've seen how atoms bond together, we can have a look at how molecules are shaped and once these bonds are formed. So to do this, we have to mention electron pair repulsion theory, which states that electron pairs orbit the central atom of a molecule or ion while wanting to stay as far away as possible in a sphere shape. So basically, electron pairs repel each other and try to stay as far away as from each other. So this gives us this diagram, which looks at, depending on the number of electron groups and the number of lone pairs of electrons, what a molecule will look like. And the easiest way to understand this is through example. So I've taken here 4 examples. So carbon monoxide has a linear shape, water has a bend shape, ammonia has a trigonal pyramidal shape, and methane has a tetrahedral shape. So to figure out the shape of a molecule, we have to know the number of valence electrons. For example, oxygen has 6 valence electrons, carbon has 4. This gives us the Lewis structure, which is on the second column here. And knowing this, we can simulate the 3D shape of the molecule, which is in the black background on this slide. And that's why carbon dioxide has a linear shape with these two bonded atoms of oxygen. If we look at water, for example, what's interesting is that oxygen is also bonded with two atoms, here 2 atoms of hydrogen, but oxygen also has 2 lone pairs of electrons in this molecule. So if we look at the 3D shape of the molecule, we can see these lone pairs of electrons take a lot of space. However, when looking at the shape of a molecule, we actually ignore those lone pairs of electrons. So the final shape of the molecule is this sort of triangle here that is called a bent shape. It's a similar idea for ammonia, which is linked to 3 atoms of, where the central atom of nitrogen is linked to 3 atoms of hydrogen, but also 1 lone pair of electrons. So this means the shape, the lone pair repels the other electrons, and the final shape is this trigonal pyramidal shape. And finally, methane. The central atom doesn't have a lone pair of electrons, but it's linked to 4 hydrogen atoms, therefore the shape is tetrahedral. Obviously, this will change for ions compared to molecules because they'll have gained or lost electrons. So, for example, looking at how ammonia in water will create some ammonium ions and hydroxide ions, we can see that this extra electron, missing electron, actually influences the shape. So, hydroxide ion, because it only has 2 atoms, the shape will always be linear, but we can see that it still has these 3 lone pairs of electron around the oxygen atom. And the ammonium ion actually is linked to 4 hydrogen atoms and no lone pairs of electron, which means that the shape is tetrahedral, whereas ammonia, which we saw just earlier, was trigonal pyramidal. So we now know how atoms bond together, and we'll look at how molecules bond together. Intermolecular forces in general are weaker than electrostatic interactions between atoms, but we'll see here one of the main types is dipole-dipole interaction. So a dipole is a polarized object. That means it's an object with a neutral overall charge, but containing a positive side and negative side, or as you can see in the diagram here, partial positive charge and a partial negative charge. This is caused by an unequal sharing of electrons, for example, if there's a difference in electronegativity. And there's different types. So, for example, London dispersion force, is a type of induced dipole-dipole interaction where the proximity of other electrons in neighbouring atoms create temporary dipoles and therefore temporary attraction forces. It is, however, the weakest of intermolecular forces, whereas the strongest is hydrogen bonding, which is a specific permanent dipole-dipole interaction. We also have ionic bonds, which we've already talked about, which also work between molecules. Now, the strengths of these different intermolecular forces have different implications on the physical properties of the substances. So, stronger intermolecular forces mean that a substance is more likely to be liquid or solid at room temperature. And this is what also allows us to create substances that are sticky or to create sticky tabs. All of this comes from these forces. On the other hand, weaker forces mean that a substance will most likely be a gas at room temperature. And finally, ionic compounds are more volatile, so will need to be sealed properly. So we'll now just go through a brief overview of what we talked about. So, electronegativity is what drives bonding between atoms, and these different bonds, so covalent, ionic, metallic, will determine the different physical properties for the different substances. We've also looked at the shape of molecules and how molecules bond together with dipole-dipole interactions, and how this determines how substances behave and any specific requirements when handling them. So to go back to the sample that we have, fluorine is a gas at room temperature. It's also the most electronegative element in the periodic table and the most reactive. It will need to be stored completely separately from others as it reacts with water and creates highly corrosive compounds. Krypton is also a gas, but it's a noble gas, so very stable and inert. It does, however, react with fluorine, so again, important to keep them separate. Now, silver is a metal. It's solid at room temperature. It can, however, react with other elements, so again, precautions should still be taken. And lastly, barium is an alkaline metal, also solid at room temperature. However, it is highly reactive, especially with air and water, and it will also form toxic compounds. Again, this just really confirms how important it is to take all the necessary precautions when handling those. Thank you.